The pneumatic system supplies bleed air to anti-ice systems, air conditioning packs, and to pressurize the potable water tank. The pneumatic system control functions are integrated with anti-ice and air conditioning functions through the air management system. The air management system controller has 2 channels, and in case of failure, one channel is able to control the entire air management system, including both ECS packs, bleed systems, both wing and engine anti-ice systems, cabin and flight deck temperature controls, cabin pressure control, and the entire bleed overheat detection system. The pneumatic system sources are engine bleed air, APU bleed air, and high-pressure external bleed air. Engine bleed is controlled through bleed port selection, pressure regulation, and temperature control. The system is protected against over-temperature and over-pressure, and monitored through a manifold leak detection and fault localization system. The bleed system status indication has 3 main displays: the Central Maintenance Computer (CMC) indications, Engine Indication and Crew Alerting System (ICAS) indications, and ECS Synoptic page. The CMC indications are used by the maintenance personnel to determine the faulty component. The ICAS indications are used by the crew for flight safety. The ECS Synoptic page provides the crew with an overview of system status. The synoptic pages cannot be used to generate crew actions or used in any action generated by the ICAS. The electronically controlled bleed air system provides control, electronic sensing, internal logic, and built-in test, achieving improved reliability and dispatchability. The control components provide bleed flow selection between the high-pressure and low-pressure engine bleed ports, and regulate the bleed pressure prior to delivery to the pneumatic system bleed air manifold. Torque motor controllers provide servo air control, and electronic pressure sensors and temperature sensors provide accurate analog signals. A left and a right-hand system is provided, and each AMS channel can control the entire AMS. The pneumatic system provides cross-bleed management, including cross-bleed engine starting capability, operation of both ECS packs, and operation of slat anti-ice systems during either single-engine or APU operation. An APU bleed valve and an APU check valve allows for APU bleed supply to enter the bleed manifold, which is shut off and closed by engine bleed pressure when APU is not running. A high-pressure ground connect check valve allows high-pressure ground cart supply to enter the bleed manifold and is closed by engine bleed pressure when a ground cart is not in use. The cross-bleed isolation valve is driven by a pneumatic actuator and controlled by a servo pressure signal provided by the torque motor. Duct pressure is ported directly to the piston of the actuator from either upstream or downstream of the butterfly disc, through a ball selector valve that transmits the higher pressure, and through a filter to the torque motor, The supply pressure force, along with the actuator spring force, provides the closing force for the butterfly disc. The opening force is provided by servo pressure acting on the larger servo piston. With servo pressure low, the valve is closed. As servo pressure increases, the valve opens. A closed valve position switch provides position indication for built-in test purposes, indicating a fully closed or modulating valve. The crossbleed valve is fail-safe closed, but can be locked in open position. The crossbleed valve will open under the following conditions: left supply enabled, right demand, no right-hand source. Or left supply enabled, right engine at start. Or right supply enabled, left demand, no left source. Or right supply enabled, left engine at start. Left supply enabled if bleed switch is in auto and left manifold pressure is more than 20 psi. And no leak on either side. And right EMBRAER SOV mode closed. And right flow command is valid. Right supply enabled if switch is in auto and right bleed available, and left flow command valid, and left EMBRAER SOV mode closed, and no leak on either side. Left supply is enabled for right-hand engine start if switch is auto and left engine bleed available, or left manifold pressure is higher than 45 psi, and right engine status at start, and right-hand EMBRAER SOV mode closed. Right supply enabled for left-hand engine start even if leak is present, if switch is in auto and right-hand bleed available, and left engine status start, and left EMBRAER SOV mode is closed. Crossbleed valve opening inhibited if left HPSOV open and right-hand manifold pressure is higher than left-hand manifold pressure, or right HPSOV open and left-hand manifold pressure is higher than right-hand manifold pressure. As a built-in test function, 2 minutes after landing, the left AMS controller channel commands the crossbleed valve open and closed. The right AMS controller then commands the crossbleed valve open and closed. Whenever either side, left or right bleed, is disabled, a message is transmitted to the ICUS to indicate that the airplane altitude must not exceed 31,000 feet. The pneumatic bleed lines running from the engine bleed ports and ram air inlets through the pylon enter the wing leading edges and run toward the packs. The ECS is installed at non-pressurized location under the midsection of the fuselage, under the wing-to-wing fairing. The pneumatic bleed lines are installed in this area. Only conditioned air will enter the pressurized cabin. The ozone converter is located upstream of the flow-sensing venturi. Air exiting the bleed system passes through the ozone converter before entering the air conditioning packs. There are 2 ozone converters per aircraft in each side of the pneumatic system. The ozone converter contains a catalytic material, which through a chemical reaction converts ozone to oxygen. This reduces the amount of ozone in the air entering the air conditioning system. The engine bleed air control components provide bleed flow selection between the compressor 9th stage and compressor 5th stage engine bleed ports. The compressor 5th stage air pressure is insufficient at lower engine power settings, and compressor 9th stage air pressure is too high at higher engine power settings. The components which are installed into the engine bleed system are high-pressure shut-off valve, the nacelle pressure shut-off valve, the low-stage bleed check valve, the torque motor controller, the pre-cooler, and the fan air valve. The high-pressure and low-pressure stage switching control is based on a soft switching logic, which uses the high-pressure shut-off valve as a pressure regulator instead of an on-off valve. The control logic regulates high-pressure air supply to scheduled 45 psi for aircraft altitude below flight level 250 and 35 psi above flight level 250 for the downstream users. As high-pressure and low-pressure supply pressures rise, the high-pressure shut-off valve regulates towards closed to maintain downstream manifold pressure. When low-pressure air rises above the desired manifold pressure, the high-pressure shut-off valve will regulate closed, and the nacelle pressure regulating and shut-off valve begins to regulate air to maintain the desired manifold pressure. However, when wing anti-ice is active, the high-pressure shut-off valve will be regulated open as needed to maintain a minimum manifold temperature of 450 degrees Fahrenheit. In this switchover region where low-pressure supply pressure is insufficient to meet the desired manifold pressure, or additional temperature is required for anti-ice operation, bleed flow is supplied by a mixture of high-pressure and low-pressure air sources. Note that the HPSOV is always closed when the HPSOV high-power close signal is received from the FADEC. The shut-off valve position is controlled by the torque motor controller. The shut-off valve is powered by a pneumatic actuator. The valve is used in 2 separate applications in the bleed system. When installed in the high-stage bleed duct, the valve, in conjunction with the remotely mounted torque motor controller, regulates the high-stage air supply to the bleed system. When installed in the bleed air manifold, the valve, in conjunction with the remotely mounted torque motor controller, regulates the low-stage air supply to the bleed system. When the high stage is selected, the regulation set point of the manifold valve is set at approximately 5 psig higher to allow for soft switching between the high and low stage bleed ports. In either case, the valve position is controlled by a pneumatic servo signal received from the appropriate controller. Duct pressure is ported directly to the supply or third area piston of the actuator. This pressure force, along with the actuator spring force, provides the closing force for the butterfly disc. The opening force is provided by servo pressure acting on the larger servo piston. Servo pressure is controlled remotely. With servo pressure low, the valve is closed. As servo pressure increases, the opening force increases until the point when net opening force exceeds the combined closing force, and subsequently the valve opens. The valve will regulate downstream pressure until servo pressure increases to fully open the valve. The valve is fail-safe closed and can be mechanically locked in the closed position. The low-pressure check valve is a dual-flapper, duct-mounted check valve. Frame and flappers are made from Inconel and are hinged in the center of the check valve frame with a pin to prevent reverse flow of high-pressure bleed air into the engine low-pressure supply port. The nacelle valve controller is mounted in the pylon with pneumatic pressure lines routed to high-pressure and nacelle valves. It is a dual-torque motor controller which controls servo air pressure to the high-pressure bleed valve and nacelle pressure regulating valve. It receives control signals from the AMS controller and from the cockpit control panel. The engine bleed system provides closed-loop electronic control of left and right engine bleed temperatures. Engine bleed air is cooled in the pre-cooler using cold fan air. The temperature of the bleed air exiting the pre-cooler is controlled by the amount of cold fan air flowing across the pre-cooler. The AMS controller receives electronic feedback from the manifold temperature sensor to determine actual temperatures exiting the right and left bleed systems, and from the temperature sensor downstream of the anti-ice valve to control duct temperature when anti-ice is on. The AMS controller will send a command signal to the torque motor of the fan air valve to regulate the flow of cold fan air across the pre-cooler. The manifold temperature is controlled to 400 degrees Fahrenheit, 204 Celsius, under normal operating conditions. The manifold temperature is controlled to 450 degrees Fahrenheit, 232 Celsius, when slat anti-ice flow is required. If temperature rises above 450 degrees Fahrenheit, 232 Celsius, for more than 2 minutes, or greater than 500 degrees Fahrenheit, 260 Celsius, for more than 10 seconds, the affected system will shut down. The pre-cooler is an air-to-air heat exchanger that cools bleed air by fan air when the fan air valve is open. The pre-cooler provides outlet air temperature at 400 degrees Fahrenheit, 204 Celsius, under normal operating conditions, 450 Fahrenheit, 232 degrees Celsius, during single-engine anti-ice, and 450 degrees Fahrenheit, 232 Celsius, and 500 degrees Fahrenheit, 260 Celsius for less than 2 minutes under failure conditions. The engine bleed air is cooled in the pre-cooler using cold fan air to remove the heat during low ambient flow conditions, such as ground operation. The fan air modulating valve is a pneumatically actuated butterfly valve, electronically controlled by a torque motor. Increasing torque motor current will cause the valve to close. The butterfly valve has a disc and shaft set installed in the valve housing. The valve shaft is connected to the actuator by a crank and linkage. In the event of an electrical system failure, the valve is spring-loaded open. The APU supplies air to the aircraft pneumatic system, which is used for air conditioning, cabin pressurization, and main engine starting. The APU bleed air is connected to the left-hand manifold and can supply both packs. The APU flow is controlled via the APU bleed valve and by the two pack flow control valves, FCVs. The flow schedule is determined as a function of ambient temperature, zone reference, and actual zone temperature and pressure. There is an override control loop in the AMS that responds to the APU exhaust gas temperature, EGT, signal from the APU FADEC. The APU bleed system contains an APU bleed shutoff valve and an APU bleed check valve. The APU check valve allows APU bleed supply to enter the bleed manifold and is closed by engine bleed pressure when the APU is not running. The on-off bleed valve is a 4-inch diameter, pneumatically actuated, solenoid-operated on-off butterfly valve. Positive indication of the valve in the open position is provided to the crew through an ICUS message. When bleed air is requested and upstream pneumatic pressure is available, the solenoid is actuated, which allows filtered high-pressure upstream air to fill the actuator cavity. Force acting on the piston, which is linked to the butterfly plate, moves the valve to the open position. When the valve is commanded closed, the solenoid is closed, allowing the piston cavity pressure to vent to ambient, and the spring-loaded piston moves the butterfly valve to the closed position. The APU bleed request is controlled by the AMS to command the APU FADEC to open the APU bleed valve. The APU bleed is commanded on if control panel APU switch is on, and the APU ready to bleed RTB signal is true, and no left bleed duct leak, and left bleed system is not enabled, and left flow demand is true, or right flow demand is true, and right bleed system is not enabled, or right engine status is start, or left engine status is start. Transition of the APU bleed request from closed to open will be inhibited if any of the following conditions are true. Left HPSOV is open, or right HPSOV is open and cross-bleed valve is open. When a bleed system is enabled, the commands to the HPSOV and NAPRSOV are based on the corresponding valve mode and control laws integrated in the AMS controller modules. When a bleed system is disabled, the HPSOV and NAPRSOV are commanded closed. The left bleed system is enabled if all of the following conditions are true. Left engine bleed is available. Left bleed switch is on. Left bleed system has not detected an overtemperature, internal or external to the duct, or overpressure condition. Left manifold pressure sensor is valid, and one of the following conditions is true. Left flow demand is true, or right flow demand is true, and the right engine bleed source is not enabled, or right engine status is start. The right bleed system is enabled if all of the following conditions are true. Right bleed switch is on. Right engine bleed is available. Right bleed system has not detected an overtemperature, internal or external to the duct, or overpressure condition. Right manifold pressure sensor is valid, and one of the following conditions is true. Right flow demand is true. Left flow demand is true. The left engine bleed source is not enabled. The APU is not enabled, and the left engine is not in start. Left engine status is start. An engine bleed source, left or right, is available if all of the following conditions are true. Corresponding control panel bleed switch on. Corresponding engine status is ready to bleed. No corresponding bleed duct leak. No corresponding over-temperature fault. No corresponding overpressure fault. No corresponding bleed shutdown fault. The EMBRAER SOV control modes are fully closed, pressure regulating, anti-ice temperature regulating, anti-ice pressure regulating. The left or right HPSOV has the following control modes: fully closed, pressure regulating, anti-ice pressure regulating, anti-ice temperature regulating. The EMBRAER SOV is declared closed if all of the following are true. Corresponding engine is ready to bleed. With the cross-bleed valve closed, corresponding left, right manifold pressure indicates the EMBRAER SOV is closed. Corresponding left or right manifold temperature indicates the EMBRAER SOV is closed. On the left side only, the APU bleed valve must be closed before checking temperature or pressure in the manifold. The EMBRAER SOV is declared open if all of the following is true. Corresponding engine is ready to bleed. With the cross-bleed valve closed, corresponding left or right manifold pressure indicates the EMBRAER SOV is open. Corresponding manifold temperature indicates the EMBRAER SOV is open. On the left side only, the APU bleed valve must be closed before checking temperature or pressure in the manifold. The HPSOV is declared closed if all of the following is true. Corresponding EMBRAER SOV is open. Cross-bleed valve is closed. Corresponding manifold temperature is less than engine LP temperature. The HPSOV is declared open if all of the following is true. Corresponding EMBRAER SOV is open. Cross-bleed valve is closed. Corresponding manifold temperature is greater than engine LP temperature with hysteresis. The hot air leak detection system is comprised of multiple overheat sensor loops and electronic control. Together, these components provide rapid and reliable overheat and leak detection for the bleed air distribution manifold and anti-ice supply ducting. The overheat detection system includes 6 different loops in 7 different areas. APU duct detection loop, left bleed duct detection loop, left anti-ice duct detection loop, right duct detection loop, right anti-ice detection loop, and an optional loop for second trim overheat detection. The overheat signal is used for crew alerting and to isolate the appropriate duct sections either automatically or by crew action. Each loop is duplicated and runs parallel to the bleed ducts. The fin wall sensor loops include outer and inner conductive materials, which are independent electrical circuits. The area between the outer and inner walls of the loops are filled with salt. If the temperature of the loops rises above 125 degrees Celsius, the circuits develop a short. A signal is sent to the ODS cards installed in the AMS controller module, and the respective system will be shut down. AMS can define the failure location within 3 inches. The system will reset if the temperature drops below the set point and the control switch is cycled. If the left manifold or right manifold ODS loops indicate a failure in either the left or right bleed duct system, or the left or right air conditioning duct system, then the respective bleed system is shut down. This action also shuts down the slat anti-ice system, the ECS pack, and the crossbleed valve. A message is sent to the ICUS. If the left manifold flight deck pack ODS loop indicates a failure in the left manifold ducting system when the high-pressure ground connection is active, a message is sent to the ICUS to indicate the failure. If the APU ODS loops indicate a failure of the APU duct system, then the APU bleed request signal is set to false, and a message is sent to the ICUS. In response to the ICUS message, the SPDA monitors the position of the APU bleed SOV. If the APU SOV does not close within 5 seconds after the ICUS message is received, the SPDA turns off the power to the APU FADEC. This has the effect of shutting down the APU and thereby the hot bleed air source. The manifold pressure sensor is a dual-element absolute pressure sensor that is used to monitor bleed manifold duct pressures. The sensor provides an electronic signal to the AMS controller, used for system control and health monitoring. The sensor is hermetically sealed and consists of a supply pressure port, an internal pressure transducer, and an electronic output connector. With a 28-volt DC excitation voltage, the sensor will provide an output voltage signal of 0 to 9 volts DC via ARINC 629 bus. The pressure sensor overpressure set point is 178 psi. The manifold temperature sensor is a dual-element RTD, resistive thermal device type sensor, and contains a platinum temperature sensing element housed in a steel probe shield. The electrical resistance of this temperature sensor increases with increasing temperature. The changes in resistance result in voltage changes across the sensor. The AMS controller determines the bleed manifold temperature by monitoring these voltage changes via ARINC 629 bus. If temperature in the manifold increases above 450 degrees Fahrenheit for more than 2 minutes or 500 degrees for 10 seconds, the respective system will be shut down.